So make sure you're here. I'm going to go with a different microphone today. I used this in the past. It's wireless. So I'm going to keep that little, you see my little voice thing up there? If anyone sees that thing flatline out during class, let me know. I know you're not going to be paying attention to it, but if you kind of look up there and see it's no longer registering my voice, let me know. I'm going to move it down here so we can see it. All right? We'll see how it works. Let's look at this first question. I'm saying find the sum, and when I say find the sum, that means that it either converges or diverges. Here, it's going to converge, so I want to know what it converges to. That's different than the second question, which says, does this converge or diverge? That's only asking, does it converge or diverge, right? So for the first one, it is a geometric series. But for all geometric series, we have to have one of two formulas. N equals 1 to infinity, AR to the n minus 1, or the other formula is sum, N equals 0 to infinity, AR to the n. So our formula is not that form yet because we start our index at 3. So the way that I showed you to do this is as follows. We need to get that index to be either a 1 or a 0, and it's your choice. So let's take a vote. For the people who actually did change the index, how many of you did it to a 1? Okay, how many did it to 0? Okay, so I'll go with 1 just because there's more people that did it that way. So if I want this 3 to become a 1 instead of a 3, I need to take 2 away from it, right? So I need my n to turn into an n plus 2. And the reason is that if I put an n plus 2 on that side right there, if that n becomes n plus 2, then the equation becomes n plus 2 equals 3. Subtracting 2 from both sides, I get n is 1. So everywhere I see an n, I replace it with n plus 2. So let me rewrite this series. Sum n equals, what's it going to be? 1. I've already done that replacement, okay? To infinity, 2 to the n, I'm replacing n with n plus 2. And then on the bottom, 3 to the, that n's going to be replaced with n plus 2, but then what was still down there? Plus 1. So my geometric series becomes sum n equals 1 to infinity, 2 to the n plus 2 over 3 to the n plus 3. Now I need both of those to be, those powers can't be n plus 2s, they have to be n minus 1s. So to make them n minus 1s, I go 2 to the n minus 1 plus 1, but I already had plus 2. So I introduced a hidden 0 there, right, that yellow, minus 1 plus 1. And then the other one on the bottom, do the same thing, 3 to the n minus 1 plus 1, but I already had down there plus 3. So again, introducing my hidden 0 there. Which means I have sum n equals 1 to infinity of 2 to the n minus 1 over 3 to the n minus 1. Now what did I still have up top though? That 2 right there, that 2 is going to be squared. Well, sorry, no. The 1 plus the 2 is going to be 3, right? So 2 cubed, so 8. And on the bottom, the 1 and the 3 come together to be a 4. So I'll have times 3 to the 4th. This is the same as what? 2 over 3 to the n minus 1. So we're here. We're basically at this point. I have an 8 over, what's 3 to the 4th? 81? 3 over 81. And then I have my 2/3 to the n minus 1. I have n equals 1 to infinity, and that is a perfect geometric series now, right? I have my n starting at 1. I have my n minus 1. I have my r. I have my a. Got it? So the answer to this is, since r equals for us 2/3, and the absolute value of that is less than 1, it converges, right, to a over 1 minus r, which for us is, I'm kind of running out of room. I'll do it. Where can I do it? I can't move this thing down. Well, I guess I can move it a little bit. That's the end of the page right there. This becomes a, which was 88 over 81, over 1 minus r 2/3. That's 8 over 81 over 1/3, which is 8 over 81 times 3 over 1, which is 8 over 27. 8/27. The moral of the story here is that everyone here should be able to identify a geometric series, change an index, and find a sum, right? Changing of the index is a big deal for me. Now, the second problem, were there any questions on that, by the way? Anything? Where's my copy? Where's this copy? Yes. Yes. That's the invisible zero. Yeah, you have to make this right here become an n minus 1. So the only way to put a minus 1 here is to add a 1 also. Now you could have just gone straight to n minus 1 plus 3, because n minus 1 plus 3 is still n plus 2. But I'm trying to show that hidden zero. All right, so the next one, oh wait, I just went through the trouble of doing that. Let me paste it then. Okay, this one, does it converge or diverge, and explain why? I was hoping that you would attack this with the comparison test. So what I'm going to do is I'm going to say my a sub n is this. Notice I wrote a sub n, okay? A lot of people, I already noticed, turned it in and said, oh, because a sub n is less than b sub n. Well, I don't even know what a sub n and b sub n are if you don't tell me what they are, right? So we want to get precise with our notation here. That's what a sub n is. I'm going to choose my b sub n to be something. And I saw people choose different things. Some people chose 1 over 3 to the n, which would be what type of series if I add those up? One more try. No. Geometric. The power is, the exponent is the n, right? That's geometric. R being what? 1/3. Does that converge? If I add those up, yes, those converge. So I could have used that, or I could have used, some people use 1 over n squared. What type of series would that be if I add those up? That's p series, with p being 2, and that converges, right? Either event, those two to compare to would be something I know about, right? So let's do a vote for those people who did do this one. How many of you used the 1 over 3 to the n? Anyone use that one? Use that one? Okay. Anyone use the 1 over n squared? Okay, we'll go with that one then. Okay, so I'm going to let my b sub n, let b sub n be equal to 1 over n squared. Now, let me compare these two sequences, all right? What is the relationship between a sub n and b sub n? The question is, what's the inequality between the two? So let me write down what a sub n is. Let me write down over here what B sub n is. And what is it? A sub n is less than B sub n. Now, the reason why is because the numerators are identical. This part of the denominator is the same, but 3 to the n is going to be some number, some big number, right? Like, well, it could be 3, it could be 9, right? Any power of 3. So if I add that over here to n squared, this becomes bigger, which makes this fraction smaller than that one, right? So this is true for all n, right? That's true for all n. So that means A sub n is less than B sub n. Now, if you look at your comparison test, right? Look at your comparison test. When A sub n is less than B sub n, what do you have to have happening with B sub n? The series. It converges, right? And does our B sub n converge? Yes. Then we're going to be able to use this test. Okay, so A sub n is less than B sub n, and we have that the sum of B sub n, or the series, which is 1 over n squared, is a p-series with p being 2, which is greater than 1, thus it converges. I'm writing this out, and that's what I expect to see from you also. Don't just give me this inequality and say it converges, because that doesn't tell me you understand anything about why it converges at all. So A sub n is less than B sub n, and the B sub n is a p-series with p being 2, which is greater than 1, which means it converges. Therefore, our final result from the comparison tells us what? Sub A sub n, or sum A sub n, which for us is our series. What the hell was it? 3 to the n converges by the comparison test. Okay? That's what I'm looking for. Now, you could have done this problem exactly the same using geometric. It would have worked. If you had used the 1 over 3 to the n, it would have worked the same way. Because the left side still would have been less than the right side, and the B sub n would have been a geometric series with r being 1/3. That would have converged, which forces the A sub n to converge. Alrighty. Moving along. Where did I put my notes? I have a bunch of stuff I've graded. I've tried to update your grades, so you might want to go look at those. All right. I want to hand stuff back. Hopefully I'll remember today. Okay, we're going to start today with the next section. So we're kind of done with our, we finished 8.3. 8.3 had two, oh wait, hold on, we didn't do limit comparison. I knew there was something I was missing. There was one more part of 8.3 that we needed, limit comparison test. You have my sheet? Can you share with him until, all right. All right, so continuing from last time, we now talk about the limit comparison test. Now this is on your sheet. It's actually under the comparison test. Do y'all see under comparison test? It's the third one down there. It says if the limit as n goes to infinity of a sub n over b sub n is equal to c, which is greater than 0, then both series converge diverge. So let's do an example so you can see how this is going to work. Let's take a look at as an example, sum n equals 1 to infinity of 1 over 2 to the n minus 1. Now, I could try the traditional comparison test right now, couldn't I? I could try coming up with a b sub n and try and see which one's bigger, right? Which one's bigger, and then try and use that test. But this is a slight adaptation of that test that allows me to try and attack it in a slightly different manner. I still have to come up with something to compare it to, which in this case, what do you think would be good to compare it to? How about if I let, I'm going to let my, of course, a sub n be what's in there, 1 over 2 to the n minus 1. But then I'm going to choose my b sub n to be 1 over 2 to the n, which is same as 1/2 to the n. Now, do you know anything about b sub n? If I take the sum of all those, what type of series would that be? I'm taking 1 over 2 to the n and forgetting that the 1's there. That's what I'm going to compare it to. What type of series is that? Geometric. R being half, that would converge, wouldn't it? So if I kind of know that's starting the problem, I'm going to compare it to that. But instead of trying to set up that inequality a sub n and b sub n, trying to see which is greater or less or anything like that, I'm going to set up a ratio and take the limit as n goes to infinity. That's what this third part says. So all we have to do now is find the limit as n goes to infinity of which one over which one? A sub n, which is 1 over 2 to the n minus 1, over b sub n, which is 1 over 2 to the n. Do you all agree with that? Now, that's just a fraction over a fraction, so I'm going to flip it. I get 2 to the n over 2 to the n minus 1, which is, what happens if you let n go to infinity here? Infinity over infinity, don't you? Infinity over infinity. Now, you might want to apply L'Hopital's rule here, right? You could. But you'd have to step back to what we talked about when we talked about sequences, that as long as these are functions that are defined as real functions, then you can do L'Hopital. Is 2 to the n comparable to a real valued function? It's an exponential function, right? So you could do L'Hopital top and bottom here, right? L'Hopital, which means derivative top and bottom. I'm going to do it slightly different, just so you can see it. Instead of L'Hopital, I'm going to basically divide everything by 2 to the n. So I'm going to take every term here, here, and here and divide all of them by 2 to the n, which is the same as multiplying by 1 over 2 to the n on top and bottom. And what I get is a 1 over 1 minus 1 over 2 to the n. Do y'all understand that, what I did there? Now let n go to infinity. This goes to 0 right here, doesn't it? And that means the result would be 1. And according to the limit comparison test, if that answer is a number that's bigger than 0, right, what does that tell me? Both converge or diverge. That means whatever one of them does, the other one does. That's what that means. They both go, whatever they do together. But the b sub n that I chose, right? But the b sub n, that series is geometric, with r being less than 1. Agreed? So it converges. Thus, it converges. Which means what? Therefore, my series, the one I'm trying to look at, converges also by the what we call limit comparison test. Nope. We don't know anything about what it converges to. All we know is that they go together. Like what one does, the other one does. It's like if one's a boy, the other one's got to be a boy. If one's a girl, one's a girl. We don't know exactly anything else about it. Just categorically, it's convergent. Does that make sense? So the limit comparison is much like the comparison, but you avoid having to make that inequality, right? You avoid that. Not always. Sometimes it's easier to do it the other way. Sometimes this is easier. It'll just depend on the problem. Just realize this is part of what you have now in your arsenal. Okay, any questions on that? All right. Now we can start with the next section. So I have a definition to start today. I told y'all series was going to be serious business, right? I mean, you see what I mean kind of now, a little bit? And this is different than just very mechanical math where it's just like, okay, do this operation followed by this operation. It's very much having to think through what you're presented with, right? It's different animal. All right, so here we go. This is a definition. This is not a test, okay? I'm not giving you a new test that come off this sheet. This is a definition. All right. Given a series, okay, given a series, consider the series of the absolute value of your sequence. So you may have a sequence here, A sub n, that might be positive terms or negative terms, right? This guy right here. That might have positive or negative terms. They might oscillate back and forth. I want us to look at just taking the absolute value of that and considering basically all those terms, but all positive. With me? If the sum of the absolute values of the terms converges, then the original series is called absolutely convergent. Quote, absolutely convergent. That's the definition. So that's a definition of absolutely convergent. Now, I remember when I first learned absolute convergence, I thought that absolute convergence meant like this series like converges all the time. It's absolutely convergent. I was thinking of the word absolutely like to mean always, and that's not what it is. This says, look, if you have some series, all right, then if you look at the absolute value of all of its terms, and if that converges, then the original series is just called absolutely convergent, meaning its absolute value of its terms converges. That's all. So it's not like some super convergence, absolute convergence. It's not that. With me? All right, let's look at an example. Let's look at 1 minus 1/4 plus 1/9 minus 1/16 plus 1/25 minus dot, dot, dot. Talk about whether this is absolutely convergent or not. Okay? I want us to talk about whether or not this is absolutely convergent or not. What do you notice is happening with this series? It's alternating, right? We call this an alternating series because the terms are alternating signs. Can anybody help me generate the summation notation of that series? Sum, let me start, n equals 1 to infinity. They alternate starting with positive terms. How do you create an alternating sequence with positive terms coming first? -1 to the n plus 1 or n minus 1 would work. We discussed that a while back. That'll create alternating starting with positive. And then what do all the other terms have in common? 1 over n squared. Good. Times 1 over n squared. I think one of your homework problems was like that, wasn't it? Any questions on that? We're all okay with that series? Agree that that creates that series? Alternating. So does anybody recognize this series here? 1 over n squared is what? P series. But we never had this alternating part in front. See, that's different because alternating means you have a positive term, then a negative, so you take some away, and then you add a little bit and take away, and then add and take away. So the result of this is it may be completely different than if that wasn't there. It might be. It depends on the series itself. So we're not here to, we cannot at this point say this is a P series because of this piece, the alternating part. But to talk about absolute convergence, what I want to do is look at the absolute value of the inside. And what's going to happen when I look at the absolute value? Sum n equals 1 to infinity of the absolute value of this. It'll just be what? 1 over n squared, because the absolute value, that -1, won't matter anymore, because I take the absolute value of it, it's 1. So this is just equal to sum n equals 1 to infinity of 1 over n squared, which is P series, P being 2, which is greater than 1, which means it converges. Notice also, I'm not saying that this right here is equal to this, right? What I'm saying is this, let's look at this and let's take the absolute value of what's inside. When I do that, that is equal to this, which is a convergent P series. So what can I say about whether or not this is absolutely convergent or not? Is that original series given to us absolutely convergent? Yes. Why? Because the absolute value of the series is convergent. What's the absolute value of that? +1, which means it's just 1, which means it doesn't need to be there anymore. That's the whole key. When you take the absolute value right here of that piece, the absolute value of -1 or +1 is just 1. So it just turns into a 1 and sitting in front of there. Wait, what? Yeah, you don't even need the to the n plus 1 anymore, because it's always going to be 1, 1, 1, 1, 1. Bless you. On any alternating series, when you take the absolute value, that alternating part is gone. Yep. Thus, but watch the way our answer needs to be written. Thus, therefore, the sum negative 1 to the n plus 1 times 1 over n squared, or if you like, 1 minus 1/4 plus 1/9 minus 1/16 plus dot 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 is an absolutely convergent series. All right, that blue is my final result. The original series is called absolutely convergent because the absolute value of its terms converges. The sum of the absolute value of its terms. It'll help us with some other tests. Yep. All right, next, I think I have another example. Yeah, let's look at this example. I want you to tell me, same thing. I want you to work this out while I take a quick break. Tell me about whether or not this is absolutely convergent or not. All right? In a couple of minutes, be prepared to discuss the convergence or absolute convergence of that series. That's the series, right? Alternating series, 1 over n instead of 1 over n squared here. If I take a look at its absolute value inside, then that becomes 1 over n, which is harmonic, right? This is harmonic. It's actually a p-series with 1, right? But that's harmonic. Harmonic, therefore, it diverges. So what's my final result then? Therefore, the original series, the one that I was given, right? Is what? Is not absolutely convergent. We will not say it's absolutely divergent because we actually don't even know what the sum does. Okay? This sum up here that I started the problem with, 1 minus a half plus a third minus a fourth, we don't know if it converges or diverges. The only thing we know is that the absolute value of its terms does not converge. right? So it is not technically absolutely convergent. But it turns out, as we will show in a second, that the original series up there, that alternating series, converges. It's harmonic, right? But it's plus minus plus minus plus minus. When you do that to a harmonic, it converges. But we'll have to show it. We're not ready for it. Okay with this so far? All right. So that's your definition. Now, this will kind of address what you were talking about here. This is another definition. If a series is convergent, but not absolutely convergent, we call it conditionally convergent. All right. So let's just make sure we understand what this means. Let's say we're given a series, we can show it converges somehow. But then when we take the absolute value of its terms, we show that that doesn't converge. Then the original series is called conditionally convergent. It itself converges, but its absolute value pieces don't. So there are conditions to which it converges. Does that make sense or not? We'll see. I'm going to do an example, but before I can do the example, I have to give you our next big test. So here's our next test. It's called the alternating series test. This is on your page, your handout. What are the tests we have so far? What's the first test? N-term test. Then we always look, see, is it geometric? P-series, which includes harmonic. Integral test. Comparison, which includes the limit comparison. The telescopic sometimes helps us, right? That's what we have so far. Now we're adding, well, that's not a test though. Nope. This is our next test now. This is the alternating series test. So here's what it says, and we have to pay special attention to the way I write this, okay? Suppose we have a series, okay? We have some series, and that series can be looked at as having a -1 to an n b to the n, a b sub n. Actually, I don't want parentheses around that. Just do a dot. And I'm going to put up here n or n plus 1. What does that mean? Basically, I'm trying to say, look, let's say that we have some series, a sub n. This series right here alternates. Maybe it starts at negative, maybe it starts at positive. It doesn't matter, but it alternates. Then the -1 to the n or the -1 to the n plus 1 is just the part that makes it alternate, right? Then the b sub n is actually the part that's on the outside. So in the last two problems, our b sub n was 1 over n squared, was in the first example, and the next example was 1 over n, wasn't it? So our b sub n, I'm going to put down here with our b sub n being greater than 0. Meaning whatever that piece is that we peel off the alternating part will always be a positive number. All right, suppose we have that. If the following two things are true, if b sub n plus 1 is less than or equal to b sub n for all n, and this next part, the limit as n goes to infinity of b sub n equals 0, then the result of this test is the original series converges. Both have to be true. Now, I want to point something out here on this step right here. This means that it's a decreasing sequence. Remember when we talked about sequences? We said if the next guy is smaller than the one before it, smaller, 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 then it's decreasing. That's basically what that inequality means, right? If I write it the other way around, I'm saying the nth guy is bigger than the next one. And then he's bigger than the next one. And he's bigger than the next one. See that? So what we need, just to recap, to be able to tell that an alternating sequence converges is that we look at it, we peel off the part that's alternating, and we look at what's left. That part should always be positive terms. We take those things, whatever that is, and we compare it to the next one in the sequence. If that inequality holds true, or if it's a decreasing sequence, and that when we take the limit of that guy at the end, we get 0. If those two things are true, we're guaranteed convergence. All right? If they don't hold, we won't be able to determine anything. All right? The test will fail. Let's do an application of the test. Discuss or determine convergence of 1 minus a half plus a third minus a fourth plus ... That's that series we had earlier, right? It looked harmonic, didn't it? And we actually determined that this is not absolutely convergent, right? Because when we took the absolute value, it was harmonic, it diverged. We said it's not absolutely convergent. But I wonder if it itself is convergent. Well, let's see. We have sum n equals 1 to infinity. We already came up with this formula. Negative 1 to the n plus 1 times 1 over n, right? That whole thing, all of it, is a sub n, right? But the part over here, 1 over n, that's our b sub n, isn't it? That's the part that's always going to be positive. The part in front is the part that alternates. So what I want to know is if b sub n is 1 over n, if that's going to hold those two conditions that we had. So first condition, and this is a question, is b sub n plus 1 less than or equal to b sub n? Yes or no? Well, let's plug in. That's 1 over n plus 1. Is that less than or equal to 1 over n? Is that always true? Yes. That holds for all n, doesn't it? And I think we've been through this logic enough to know that the denominator on the left is bigger than the one on the right, so the fraction is smaller on the left. So this is true for all n. And now let me take the limit as n goes to infinity of b sub n, which is the limit as n goes to infinity of 1 over n, which is 0. That's my second condition. Isn't that really like the nth term test? Think about this. This is the nth term test. I'm just taking my my piece up there, that b sub n, and just letting n go to infinity. When we used to get 0, we would say we don't know anything, right? But if it's an alternating series and it goes to 0, along with this decreasing aspect of the series, we're guaranteed convergence. All right? Therefore, what? What's my final conclusion? 1 minus 2 plus 1/3 minus 1/4 converges. Well, you could write this, or you could write sum a sub n converges. But you can only write sum a sub n converges if somewhere up here you told me what a sub n was, which I did. I did say what a sub n was. But if you don't tell me what a sub n is, and then at the end you say that, I won't know what you're talking about. Well, I will, but then you get docked off because you expect me to. You understand? This is about communicating your ideas onto a piece of paper. Yeah, yeah. I mean, most math people would look at that and be like, "Oh yeah, well that's an alternating harmonic series. It converges." You just know that. But you can't, on a test, you can't just tell me, "Oh, okay, well that series converges," just because I know. You have to explain it. This alternating harmonic does. What if you had? Wait, say again. Well, what would happen there? What's 1 minus 2 plus 3 plus 4? Well, here, let me ask. Let me ask you. What is that then? What's 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus ... Try the test. This is an alternating series, right? Try the test. What's the formula? And sum n equals 1 to infinity, negative 1 to the n plus 1 times n, right? So what's b sub n for us? B sub n is n. Yeah, but the negative one's still going to make it. That doesn't get around the fact that it's still n. Is the first condition met? What's that? Yes, but this is not a p series because of the alternating part. This no. See, here's the thing: we have to be careful. This look at if these are all pluses, this diverges, and there's no question about that, right? If these are all pluses, the nth term test says n goes to infinity, right? Or you could turn it into a p series and say that it's infinite. But the negative one here creates an alternating series, and therefore you can't look at this part and say, oh, that's p series, right? You can't do that. For the same reason on the problem before, right? Look at this problem before. Look up here. What if I would have said, look at the b sub n, and I would have said that's harmonic, it diverges. It would have been wrong, right? That would have been wrong. If I would have just looked at the b sub n. I have to run this test. I don't know if am I kind of addressing that question a little bit? This test will tell me if it converges. Okay? Could you plug like a harmonic inside of a ratio test or something? Well, we haven't done the ratio test. I was wondering, like, can you use the test inside of a test? Yes. If in the middle of a test you need to see what something in there is doing, you could apply another test on that piece. Yes. Yep. All right. Be very careful with this. This series right here, we cannot just start doing tests on top of the overwhelming thing here is we have an alternating series. And if you look at this here on the table, when you go to alternating series, the comment says applicable only to an alternating series, right? So we have to use the alternating series test here. Is this true? Is the number 1 true? Is b sub n plus 1 less than or equal to b sub n? So is n plus 1 less than or equal to n? No. False. So what does that mean? What's that? Test fails. That's all. We can't determine it. Look at the test. It's kind of like, I hate to say it, but it's the only test I can think of right now is a pregnancy test. If you use a pregnancy test, right, and the pregnancy test, if it says pee on this thing for 3 seconds or whatever the hell it is, right, and you do it and the stick falls off and drops in the toilet and the test strip breaks or something, right, your test fails. Does that tell you you're pregnant or not pregnant? No, the test failed. You don't know anything. Just because the test fails doesn't mean I can say it's convergent now. Do you see what I'm saying? Or divergent. Just because the test said I'm not convergent doesn't mean I'm divergent. I don't know if that makes sense. It's a logical thing here. Test fails means you don't know anything. So you'd be stuck. Yeah, you need to go buy another pregnancy test or use a different one or do it correctly or something like that, right? The test failed. Or here's a better one. You take a pregnancy test to see if you have strep throat. Well, that test fails to give you any result on whether or not you have strep throat, right? So if the test comes back and says positive, you're pregnant, that doesn't mean you have strep throat. You know, this test only works, it only gives you a result if everything is satisfied. What's that? That's what I'm trying to apply it to. Yeah. All right. So the answer is, this is still an unknown question at this point. All right. Let's just wait. We might be able to handle this. All right. All right. Here we go. Where was I? Alternating series test. Oh yeah, this one right here. How about this? Sum n equals 1 to infinity, negative 1 to the n times n squared over n cubed plus 1. So this is an alternating series, right? Our a sub n is everything. Our b sub n is just the n squared over n cubed plus 1. I'm not trying to figure out if that series converges. That's not what I'm trying to figure out. I'm trying to find 2 things, right? Alternating series test says, first thing I need to show, right, is b sub n plus 1 less than or equal to b sub n. Please, I want to make a note on your formula sheet. I know this is going to be confusing, but on your formula sheet, notice that they're using a sub n instead of b sub n. They peeled the a sub n off the negative 1. Do y'all see that on your formula sheet? Or your cheat sheet here? The alternating series, they have sum negative 1 to the n, then a sub n is peeled off. The a sub n on here is like our b sub n. Is this true or not? I have to plug n plus 1 in compared to, so if I plug n plus 1 in, I have n plus 1 squared over n plus 1 cubed plus 1 less than or equal to n squared over n cubed plus 1. Is that true? Why? If the value here, n plus 1, is bigger than n, right? So this denominator is bigger than that one. Is that okay? It's not good. It's not enough. Why? Numerator got bigger too. See, they both went up. Now, if this had stayed the same, then I would agree with you. But the problem is that's going up also. So I can't really tell just by looking if this one went up faster than that one or not. So I'm starting to lose it a little bit here. Do you see that? Everyone see that? You could start messing with this. You really could, and you could start, maybe cross multiplying, and you might get somewhere, and you probably come up with a result. But here I'm gonna approach it slightly different. Okay. Remember when I gave you the note, I said that this step really meant we're trying to show that the sequence was decreasing. So the way I'm going to approach it is different. I'm going to take my sequence and I'm going to look at it as a function. And I'm going to try to show you that that function decreases. How do I show a function decreases? Take the derivative and show it's what? Other way, less than 0. Decreasing would be down. So maybe if I take the derivative of that, it'll be negative always. So I'm kind of scrapping this idea right here. What's the derivative? So you have to do quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. What can you tell me about the bottom squared? It's always positive, so I'm just going to put plus. It really doesn't matter, does it? N cubed plus 1 squared is always positive. All right, let me try and clean up that numerator. I'm kind of running out of room, so I'm doing it over here. I've got 2n cubed plus 2n minus 3n cubed all over a positive number, which is 2n minus n cubed. It's to the 4th, yeah. I don't know why I put cubed. Thank you. Y'all see that? 2n to the 4th? All I did was distributed and then put these two together. All over a positive number. Yes. But which one's bigger? N to the 4th or 2n? It should be, yeah. So if you're convinced with that, that's fine. I was just going to go one more step. I was going to factor an n out. Because I know that for all n's, right, n is always positive. So I know that's a positive, positive. The only question is this positive or negative? Well, if n is 1, it's positive, right? But if n is 2, or 3, or 4, or 5, or 6. So this is not always negative, but it's eventually negative, which is what I was alluding to last class. It may not decrease initially, but then at some point it does. And it stays that way. Exactly. So I'll say that this is less than 0 for all n greater than or equal to 2. Therefore, it's decreasing. So I've satisfied the first condition. What's the second condition for the alternating series test? Take the limit as n goes to infinity of whatever b sub n was, which for us was n squared over n cubed plus 1. Application of L'Hopital's rule twice could get you there. Or actually what? Yeah, twice. Do I need to show it or not? No? 0, okay? Or you can just divide every term by n cubed. That'll get you there also. So have we satisfied both conditions of the alternating series test? Yes. Because if you looked at it, our sequence is doing something, right? We looked at our sequence as a function instead of a sequence of dots. And we showed that after you get past 1, that anywhere past 1, that's a bad picture. Anywhere past 1, if you take the derivative, the slope of the tangent line is negative, which means it slopes down, which means that it's going down. So if you look at it just now at the integers, right, that my integers lie on that graph also, that this b sub n is bigger than the next one, which means that that inequality holds. Okay? Man. Next. Oh yeah, conclusion. Sorry. Therefore, the original series what? Converge. Don't know what to, but it converges. Well, no, that's a good comment. This was supposed to start at n equals 1 to infinity. Do I need to say that this only converges when n is greater than or equal to 2? There's something I said. It was actually going to be part of your quiz today, but I decided not to put it on it. I was going to ask you whether or not a finite number of terms affects your convergence or divergence. That's false, right? So even though the first term or maybe first 2 terms or 3 terms might not be decreasing, those are just going to be numbers. So if I have a number, and a number, and then the rest of the numbers forever add up to be something, then adding those 3 numbers still adds to something because it's finite. So we don't care. We don't care that we have to go to a certain place before we can say decrease. All right, so let's try to look at a theorem now. Theorem. If sum a sub n is absolutely convergent, then sum a sub n is convergent. Why would this be true? What does it mean for a series to be absolutely convergent? When you add up their absolute values, it's convergent, right? Then why would that force the series itself to be convergent? It's got to be smaller, right? Because you're at minimum, right, smaller. Because if you add up the absolute values, then every one of those is a positive number. And if all those add up to converge to a number, then the series by itself, without the absolute, right, might have some subtractions in there, but if everything else adds up to be a number, then taking some minuses away should still make you converge. That's kind of the idea. Here's something to be careful with, though. Careful. If this is not absolutely convergent, then that's not convergent. Do you think that's true? Yeah, this doesn't work the other way around. This theorem says, look, if it's absolutely convergent, then it must be convergent. It does not say if it's not absolutely convergent, then the original series is not convergent. So this is not true. Don't get these mixed up. So I'm going to give you an example now of how we can use this theorem. Example. Look at the sum n equals 1 to infinity of sine n over n to the fourth. See, the sine n in there, when you plug in different values of n, sine of 1, sine of 2, sine of 3, sine of 4, that's going to give you values that are going to just kind of be sporadically on the sine function, right? And therefore, you might have some of them be positive, some negative, some positive, some negative, right? So they're going to be kind of bouncing around, not even oscillating. So it's not even an alternating series in the sense that it's not positive, negative, positive, negative, positive, negative. It may not do that. Do you understand that or not? Because sine 1, 2, 3, there's no like pattern to it. If that was sine pi over 4n, then there would be a pattern. But if the fact is just n, it's going to jump around. So this is not an alternating series. It does change signs, but it's not one after the other, back and forth. Do y'all follow me on that or not? Okay. But let me try and use this theorem. If I look at the absolute value, okay, so let me look at the absolute value of this. Then every term now has to be positive or zero, correct? So it no longer has negative terms in there because it's absolute value. Now I can't pull the sine n out. It doesn't go away like the negative 1 went away. But I know that once I take the absolute value, it's going to be positive. So now I'd like to try and compare this to a series that you know about. So this is going to be my a sub n. I'm going to come up with a series that I'm going to compare it to, something I know about. How about b sub n is 1 over n to the fourth. And I'm going to use not the limit comparison, although I could. I'm just going to compare the two. I'm going to do a sub n, b sub n next to each other, figure out what's the relationship. So what is the absolute value of sine n over n to the fourth? How is that related to 1 over n to the fourth? How are they related? Which of those is bigger? Which one? What is the biggest that sine can be? 1. Any other value, well, it's between negative 1 and 1, right? But then the absolute value cuts it off even more to become between 0 and 1. So the smallest the top can be is 0, the biggest it can be is 1. So let's just say it's 1/2. Is 1/2 over n to the fourth bigger or smaller than that? Smaller, right? Do you agree? 1/2 over n to the fourth is smaller than 1 over that. So 1 is always bigger than or equal to this. The top is always bigger than or equal to this, which means this fraction is always bigger than or equal to this one, right? So this is always bigger than or equal to it. You could also multiply both sides here by n to the fourth, if that helps. Then you have absolute value of sine n is less than or equal to 1. Do you agree with that? That's true? So that inequality is the right inequality. All right, now going back to comparison test, I have that the A is smaller than the B. So I need for that B to do what? I needed for the sum of the B's to do what to use this test? I needed the sum of the B's to converge. I need to go to a new page because I'm out of room. So A sub n is less than or equal to B sub n, and I have that the sum B sub n equals sum 1 over n to the fourth is a P series. P equals 4, which means it converges. Therefore, sum, what? Absolute value of sine n over n to the fourth converges by the comparison test, right? Therefore, what? The sum sine n over n to the fourth converges by theorem. Let's number that theorem. Let's just call it theorem 8 for chapter 8. Well, let me see if they have a number for it in the book. Hold on. I'm pretty sure they do. Theorem 1. So we'll call it theorem 8. How about theorem 8.4? Because it comes out of section 8.4. Go back to that page here. Where was that? Where is it? I think I went back too far. There it is. Theorem, we'll call it theorem 8.4. By theorem 8.4. Because theorem 8.4 said if the absolute value of a series converges, in other words, if it's absolute convergent, then it's convergent. We have about 15 minutes. I think that's enough time to start the next test, ratio test. We only have 2 more tests, all right? What's that? We only have 2 more tests in here. By the way, that theorem is actually on this page. It's the one right above collapsing and telescopic. It's basically saying if the absolute value of a series converges, then the series itself converges. Right? That's what we just did. We showed that the absolute value of the sine converged, that sine of n over n to the fourth, which meant that the sine n over n to the fourth converged. All right, ratio test. The ratio test says if you have a series and if you take the limit as n goes to infinity of the ratio, absolute value of the ratio, of the n plus 1 term to the n term, if that equals L or infinity, then it converges if L is less than 1, and it diverges if L is greater than 1 or infinity. This is all on your thing here. It's called ratio test because you're taking the ratio of what does a sub n plus 1 over a sub n mean? You're taking like some term in this sequence, right? And you're taking it and you're dividing the next one by it, right? So it's the next guy divided by the one right before it. If that ratio is less than 1, it converges. If it's greater than 1, it diverges. What if it is 1? What if the ratio is 1? Test fails. It's over here in the comments. Inconclusive if L is 1. So let's see how we can apply this to an example. This is a really powerful test, all right? It's used a lot. fact, I gave you some bonus question. Remember a bonus question I gave you a while back? It was actually computing that right there. It was a limit a sub n plus 1 over a sub n. I know like 3 of you or 4 of you did it. You were actually doing a ratio test is what you were doing in that bonus problem. So here's the example. Let's talk about this series here. Now you can probably see from this that you could split it into two, and you would have geometric on the first one with 2/3, and that would converge. And then the other one, the 5 would be a constant, and then you'd have like 1/3, so that would be geometric. This would converge because of that. But I want to show you the ratio test in action on this, even though you could do it a different way. And on a test, you're free to do whichever way as long as it works, okay? So converge or diverge. Let's see. With the ratio test, I'm going to do a sub n equals 2 to the n plus 5 over 3 to the n. Right? That's what I'm going to choose. So tell me what a sub n plus 1 would be. 2 to the n plus 1 plus 5 over 3 to the n plus 1. And now I'm going to take the absolute value of a sub n plus 1 and divide it by a sub n. So what would the absolute value be? I'd have 2 to the n plus 1 plus 5 over 3 to the n plus 1. But then divide that by a sub n, 2 to the n plus 5 over 3 to the n. Absolute value of all of that. And a fraction over a fraction means you flip, reciprocal. So this is the same as 2 to the n plus 1 plus 5 over 3 to the n plus 1 times the reciprocal of that denominator, which would be 3 to the n over 2 to the n plus 5. Plus 5. Well, in a second. That's all right? This is equal to 2 to the n times 2 to the 1 plus 5 over 3 to the n times 3 to the 1 times 3 to the n over 2 to the n plus 5. So that's just using, kind of like we did with geometric series when we're trying to peel the a off. I'm just rewriting these pieces here. Oh. Right? Just rewriting that to be this. And that to be this. But what cancels here? Careful. You can do 3 to the n's can cancel there. But the 2 to the n doesn't because you have addition down there. So let's just see what we've got. I've got 2 to the n times 2 plus 5 over 3 times 2 to the n plus 5. Yay or nay? Is this, I'll distribute. How about this? 2 times 2 to the n plus 5. Just change the order on top. Absolute value. Oh, I dropped the absolute value. Why did I drop the absolute value? They're all positive. Okay, that's what I have, right? That's what I have. Now I need to let n go to infinity on this. Right, so that's just the ratio. Now let's let n go to infinity. Limit n goes to infinity of this thing, a sub n plus 1 over a sub n, equals the limit as n goes to infinity of 2 times 2 to the n plus 5 over 3 times 2 to the n plus 15. You get infinity over infinity. So you could try L'Hopital's rule, which is going to be a problem because every time you try the derivative of the top, well, no, it should work maybe first time. What is the derivative of the top? I'll do L'Hopital on this one. What's the derivative of the top? 2 times 2 to the n natural log 2. So what I'm doing here, covering up this 2, derivative of 2 to the n is 2 to the n natural log 2. But then times 2, what's the derivative of 5? 0. Down here, cover up the 3, what's the derivative of 2 to the n? 2 to the n natural log 2, right? Times 3, what's the derivative of 15? 0. So what's the bottom going to be? 3 which is 2/3. What does that tell you? Less than 1. According to, oh, I'm out of room. Therefore, the original series converges by the ratio test. I got to make sure I wrote down a sub n somewhere up here, did I? Yeah, okay. What do y'all think? I only have 5 minutes. I want to try and just set you up for factorial problem. We have not done much factorial in here, but it's really time that you see some of this. Sum of 2n factorial over n factorial times n factorial. N equals 1 to infinity. Now, before I start this, I want to make a note. We know that n factorial was equal to n times n minus 1 times n minus 2, and you do that all the way till you get down to 1. That's what n factorial meant, right? So 5 factorial, 5 times 4 times 3 times 2 times 1. Okay, here's something that you should note. N plus 1 factorial is equal to n plus 1 times n minus 1 times n minus 2. So isn't this really from here on, from here it's n minus 1, n minus 2. Isn't the rest of it just n factorial? Isn't that the same thing? Then how could I write n plus 2 factorial? As n plus 2, right? And I could go down again, n plus 1, and then I could go n and then keep going, right? When I say keep going, I mean factorial. So you can always like peel off pieces of a factorial and then the rest of it, write it down. Here's another way you might be able to see it. 4 factorial is 4 times 3 times 2 times 1, right? Well, what's 5 factorial? Well, that's 5 times 4 times 3 times 2 times 1, but that's 4 factorial. Or you could say 6 factorial is 6 times 5 times, now instead of saying 4 times 3 times 2 times 1, I say 4 factorial. But I could also have said 6 times 5 times 4 times 3 factorial. So it doesn't matter where I stopped it. Factorial means from there on. Now we need that. I'm out of time here. Let's do ratio test on this. Let's set up, oh, you know what? Let's make this a bonus problem. We're out of time. It's not bonus because it's hard. It's bonus because I'm giving you a chance to get bonus, all right? See if you can set up ratio test on that and determine the convergence or divergence of that series. Fun with factorials. All right, homework I'll email to you later on today. I feel like we have something else to talk about. Are we done or what? Yeah, use the ratio test to determine whether or not this converges or diverges. And have it ready to turn in next time for bonus.